First of all, I would like to thank to the organizers for their work and for the opportunity to present my work here. This is a joint work with Concepción Muriel and Adrián Ruiz. As the title indicates, in this work, I will present a geometric approach to finding traveling wave solutions of the generalized Korteweg-de Vries equation, or gKdV equation for short. The gKdV equation is a nonlinear partial differential equation that describes the evolution of shallow water waves. It is a well-known third-order equation that incorporates both linear and nonlinear effects, making it a fundamental model in fluid dynamics and soliton theory. This is a key example of an integrable system which was derived by Korteweg-de Vries in 1895 when trying to mathematically describe the empirical phenomenon of solitary waves in shallow water. The equation has since become a cornerstone of mathematical physics. On the other hand, the generalized KdV or gKdV equation is a more general form of the KdV equation where the nonlinearity is represented by a variable function a of u instead of the fixed coefficient 6u. This allows for a wider range of physical phenomena to be modeled. In particular, we will be concerned with the traveling wave solutions of the gKdV equation, the ones that look like a wave moving at a constant speed. And for this, we apply the traveling wave ansatz, which is this transformation here. And in this way, we reduce our original PD into this third-order ordinary differential equation. Okay. In order to solve this ODE, we will use a geometric approach based on the theory of infinity structure that me and my collaborators have developed in this paper here, and we have successfully applied in other cases. The method is rooted in differential geometry and allows us to systematically integrate the ODE by transforming it into a sequence of Pfaffian equations. As a first step, we substitute the target ODE, our goal, with the associated distribution, that is the distribution generated by this vector field set. So we are translating our ODE into a vector field in the jet space that, for purposes, you can consider R4, in such a way that the integral manifolds, the integral curves, in this case, have the form set f prime f second, being f a solution of the ODE. So our goal will be to find explicit parametrization of these integral curves, and so we would obtain solutions or prolongation of the solutions of the ODE. Okay, the notion of infinity structure, which is a generalization of solvable structures, is the key notion in this approach. It's nothing but a collection of vector field x1, x2 until xn, and it's just a way that all the distributions arising here are involutive. Remember that involutivity means that the Lie bracket of two vector fields is again inside the collection of vector field, inside the distribution. And recall also that, of course, the Frobenius theorem established that the involutivity implies the existence of integral manifolds. So we have this vector field here in R4, encoding the ODE we want to solve, and as infinity structure would be a sequence of distribution starting with the distribution generated by the vector field set, which is of rank 1 and which is trivially involutive, and all these distributions in the sequence are involutive. the first one, which is our goal, is very thin, and they are increasingly thicker. Observe that all of them has integral manifolds, and of course the integral manifold of the last one is the complete, the total space R4, and the integral manifolds of the first one is what we want. What we achieve with a symphonic structure is a kind of organization or a kind of filtration of the space R4 into a sequence of distributions, starting with the distribution set with these pink curves here, and ending with the complete space R4. Once a symphony structure is found, the process to be followed consists of the following steps. We consider the standard volume form in the jet space, and we define the one forms omega 1, omega 2, omega 3 by contracting these vector fields with the volume form. It turns out that the omega 3, the one forms omega 3 is Frobenius integrable, and we can find a first integral y3 by solving the linear homogeneous PD dy3 wedge omega 3 equals 0. So when we have I3, we consider the level sets, taking a particular value for C3. And at this point, when we choose a value C3, what we are doing is selecting a leaf of the more superficial foliation. And then we look for a local parameterization iota3 to inside this leaf. Now we restrict the remaining one forms to the level set I3 equals C3 by pulling back with this parameterization iota3. You can think of this as if we are going inside the leaf, the particular leaf that we have chosen with C3. So now we are in the same setup that at the beginning, but with one dimension less. So we repeat the process with omega 2, okay, with the new omega 2 obtained by pulling back, and repeat again and again the process. At the end, the composition of the local parametrizations is a local parametrization of the integral curves of the vector field set. So this way, we are finding a parametric expression for the solution of the ODE. Indeed, for the prolongation of the solutions of the ODE. Indeed, when we have this parametric expression, we have something of this form, set f prime f seconds, where f is the solution. But anyway, the last expression, I1 equals C1, is an implicit expression for the solution, involving only the variables z and y. And of course, C parameter, C1, C2, C3, which are the parameters of the general solution of the ODE. So, coming back to our problem, to the traveling wave solutions of the gKdV equation. We have this vector field set, and our next goal is to find a symphonic structure for this vector field. Fortunately, the vector field partial set is trivially a least point symmetry, so this distribution is involutive, given this Lie bracket condition, and so we choose partial set as the first vector field for our symphonic structure. Then we propose a second vector field x2 following this ansatz here. Okay. In many examples in our research, we have found that this ansatz works very well. Indeed, we have proven that we can always find a vector field of this form, but this is still work in progress. And we impose the involutivity condition to the distribution generated by set x1 and x2. And these involutivity conditions get translated into this system of partial differential equations for eta. It is not hard to find particular solution has this one that you can see here. And finally, for the last vector field, since we are working on R4, that is, we are in dimension 4, we can choose any vector field that is linearly independent to complete the S-infinity structure, since these 4 vector fields will be trivially involutive. And so we choose partial y2, for example. And then we have our decided S-infinity structure for the traveling wave ODE, for the gKdV. Okay, we have the vector field set and these other 3 vector fields which are the S-infinity structure. So to follow along with the method, we first write down the one forms, omega 1, omega 2, omega 3, and we focus on the last one, omega 3, which is the first Pfaffian equation we must solve. We solve omega 3 and we obtain this solution I3, which is a first integral of our ODE, and observe that the explicit expression H1 of the function H1 will depend on the choice of A. So it is here indicated. And then we focus on the level set by taking a particular value C3. I3 equals C3. We find a parametrization of this level set, which is a 3-dimensional manifold, depending on Z, Y, and Y1. Recall that at this point we can imagine something like this. And now we restrict the 3-1 forms to this level set, okay? This level set marked here. Of course, the restriction of omega 3 is 0 by definition of integral manifold. And we are left with only 2-1 forms, omega 1 and omega 2. And now we focus on this one form, omega 2, which gives rise to the second Pfaffian equation we must solve. A solution of this Pfaffian equation is shown here, and we focus, as before, in the corresponding level set by taking a particular C2. We again obtain a parametrization, in this case is iota 2, which is a 2-dimensional space. And what we are doing is going deeper in the structural formulation. We are now describing this 2-dimensional leaf, which this parametrization lets us pull back, and now we have 2 of the work forms annihilated, getting equals to 0. And finally, we tackle the last Pfaffian equation, which is shown here. A solution is given by this expression you can see here, and therefore all the solutions are given by this 3-parameter family of function given in implicit form. But remember that these are the solutions of the ODE, not the solution of the original gKdV equation. Therefore, we must undo the traveling wave transformation, and then we obtain the solution of the gKdV equation, as you can see here, in terms of the function f, which is the inverse of H3. Recall that the particular choice of the function A will determine explicit expression for H1, H2, H3, and F. So we are now going to see we're going to see particular cases of the gKdV equation when we choose particular X. For example, if we start by taking A equals 6u, with which we recover the original KdV equation, and we have these 2-parameter families of solutions which are well known. Observe that in the process we have had to take C2 and C3 equals 0 to be able to find the explicit expression of the functions S1, S2, and S3, and F, and even the parameterization iota 1, iota 2, iota 3 maybe you need to take particular values. But in other equation we have solved, we didn't have to take these particular values for theta 2 and theta 3, for C2 and C3, and then we have 3 parameter families of solution. But in this case, we couldn't. If, for example, you take A equals U squared, with this other choice, you have the so-called modified KdV equation, and our technique lets us obtain this 2-parameter family of solutions in explicit form. We can also consider A to be equal to U to the n over n. This PDE was originally called the generalized KdV equation, but then it was further generalized with a general A. And for this KdV version of the KdV, we have these 2 families of solutions with depend on the parameter c, the wave speed, and c1. And finally, if we consider A equals to alpha square root of u plus beta u, we obtain the so-called Scammell KdV equation. In this case, the infinity structure-based approach let us obtain these 2 families of explicit solutions, which depend again on C and C1. So, to recap, we start with the goal in mind of finding the traveling wave solutions of the gKdV equation. We have presented a geometric method. We use the infinity structure notion, which is a generalization of solvable structure, to integrate not this PD directly, but the ODE derived from here with the traveling wave ansatz. Recall also that this is a general procedure to solve other ODE, or in general to integrate an involutive distribution. And the geometric idea is that you have a kind of flag of foliation embedded into another. And as a result, we have a unified and general framework to derive explicit solutions for a broad family of KdV type equations. That's all. Here you have the bibliography. Thanks for your attention.
Thank you so much.